Alright, I'm going to do some special right angle triangles here, and I'm going to actually prove why they work. The first thing I'm going to do is I'm going to look at this equilateral triangle, and because I can, I'm going to say that each of the sides are worth 2a, and each of these angles are worth 6 degrees. But I'm going to put in the perpendicular bisector here. That forms a right angle, and it also cuts this angle into half, which gives me 30 degrees. Now, the base was 2a, but because it's a perpendicular bisector, it's no longer going to be 2a. It's going to be a, and I'm looking at this split here. So that's a, and this is a. And so now I need to find out what's my hypotenuse. So, or not my hypotenuse, my altitude. So I'm going to call it x. But I want to really write in terms of a. So if I did the Pythagorean theorem, I'd get a squared plus x squared equals 2a squared. Now I want you to be careful because it's the whole quantity 2a. It's not just 2a squared, it's the quantity of 2a squared. So when I do that, I'm going to use the commutative property here. I'm going to say x squared plus a squared is equal to 4a squared. And I'm going to subtract a squared from both sides. And that gives me that x squared equals 3a squared. Well, that's great, except I don't want x squared, so I'm going to take the square root of that. Take the square root of this. So that gives me x equals, it's really plus or minus, but because we're talking about a distance, we completely neglect the negative. And you're left with square root of a squared times the square root of 3. And so x equals a radical 3. And what this actually tells me, I'm going to rotate my triangle. What this actually tells me is if I have a 30, 60, 90 degree triangle, across from my 30 is a, across from my 60 is x, but we just said x was a radical 3. And across from my 90 degrees, my hypotenuse, is 2a. Well, what that technically means is this. If I had a hypotenuse of 12, I could just say, oh, sorry, and I knew that it was a 30, 60, 90 triangle. I could say, well, 2a equals 12, so therefore, a equals 6. That would mean across from my 30 would be 6, and across from my 60 would be 6 radical 3. All right, there's another special right angle triangle, and I'm going to actually erase this work here. And maybe I'll do this one in a different color. Let's see. See, it would be a nice color. See if I can do this one in red. Oops. Let me see. So if I have a square, and you'll have to use your imagination here. Oh goodness me, this picture gets worse and worse. You know what? Let's just say we have a square. And once again, I'm going to say that the sides of the square are a, and I drew a diagonal, which would mean that these both are 45 because it's an isosceles triangle. And so if and I'm going to call my hypotenuse x. So let's see what happens. I have a squared plus a squared equals x squared. Well, a squared plus a squared gives me 2a squared equals x squared. But once again, I'm trying to find the value of x in terms of a, so I'm going to take the square root of both sides. And when I do that, I'm going to flip-flop these. I'm going to get x equals the square root of a squared radical 2. So x equals a radical 2. And I'm going to get rid of this x now, and I'm going to put in a radical 2. And once again, the nice thing about this is, if I have a right angle triangle, and I know that this is 45, and I know that this is, well, even 1, this side has to be 1, because this angle has to be 45, and this would just be radical 2. It's really 1 radical 2, but the 1's understood. So that's it. Those are 2 special right angle triangles. You have your 30, 60, 90, which is this one, And you have your 45, 45, 90, which is, once I get rid of the rest of this picture, this one. And I don't know why I circled one, squared the other, but that's fine.